Good.
Oh, so many familiar places now that Yes, sorry.
Yeah. So we are starting shortly a YouTube live stream and recording. So if you do not wish to appear online, then turn off your camera and microphone. And I think we should be live.
Yes, we're live.
Good. And yeah, let me start recording. Okay, so welcome everyone. Welcome back if you were here also for the earlier talk. So we are happy to have with us Asaf Nachmias, who will give a mini course with 3 lectures today, Tuesday and Thursday about local and global structure of uniform spanning trees. So as noted, so the talks are also streamed on YouTube. And if you do not wish to appear in the videos, then turn off your camera and microphone. Everyone should be able to unmute their microphone. So if you have any questions at any point, then feel free to unmute and ask or ask on the chat. And with that out of the way, yeah, so Asaf, the floor is yours.
All right, thank you. Thanks for having me here. It's nice to be in Vancouver again. And I'm going to tell you, I guess, a long story, a 3-lecture worth of stories of about the uniform spanning tree. And this is based on several recent articles written jointly with let me just read the list of names: Noga Alon, Eleanor Archer, Peleg Michaeli, Yuval Perez, and Matan Shalev. And I will mention more or less exactly what theorems were written by whom as much as I can. So the basic setup, and I've written here in particular trees and not forests, and the basic setup, and that was to imply that I will work mostly on finite graphs. So let me just tell you what the words in the title mean. So our setup is G is a finite simple graph. Let's also assume that it's connected. And by simple, of course, I mean that there are no parallel edges or loops. Simple graph. Actually, the simplicity is not important for what I'm saying right now, but it will be important later. And T is a spanning tree. So it has to be a tree on the same vertex set as the original graph G. T is connected, right, and has no cycles. Okay, so we start with some underlying graph G and consider some spanning tree of it. Here it's customary in these talks to show this picture drawn, I believe, by David Wilson, in which you see the underlying graph is a 2-dimensional lattice, and in the white you see a spanning tree. As you can tell, it touches every site of the lattice. There's no cycles. And it's connected, so this you can check. And what you see in red is some sort of a dual of this tree, but we will not discuss it. And in fact, in what I'm going to tell you, the underlying graph, of course, will play a role in the theorems and the proof. But what is special in this picture is that you see both the tree and the graph together. Right, and it tells you something, right? You can ask, if I start with 2 points, a distance, a very large distance in the lattice, what is the length of this path in the tree? For instance, is one of the questions you can ask. this question was solved by Rick Kenyon. But in our work and what I'm about to show you, it will make less sense to show pictures like this. So the UST is connected to many topics in mathematics and computer science. And this I should also add here, I guess, loopy race walk. I noticed that it wasn't here in this list. But I'm not going to try to convince you that it's interesting because this topic has been featured before here, and that's it. Okay, so I'm just going to tell you, I'm not going to tell you about the many interesting stories that the uniform spanning tree has taken an important role. A quote that I like by Rick that he gave a few years. When was that, Rick? Right, or Rick said, the UST is a hero of probability theory, more or less. One of the heroes of probability theory, which a quote that I very like. I'm probably misquoting it. Right, so it's a topic that has a long history. In the 19th century, at least the two theorems that everybody knows about the uniform spanning tree is Cayley's theorem, right, which is not stated typically in terms of the words uniform spanning tree, just as a counting problem. The number of trees on n labeled vertices, we all know, is n to the power n minus 2, right? Or this can be seen as the number of spanning trees of the complete graph on n vertices is n to the power n minus 2. And 19th century, time didn't work very well or in the right way that we know it. In fact, 50 years before this theorem, right? This is in 1889, or 40 years before this theorem was a much stronger theorem. Kirchhoff's theorem, the matrix tree theorem allows you to count the number of spanning trees of any finite connected graph, right? So this counts the number of spanning trees of any G finite and connected, and this is a determinant of some matrix, and it's some minor of the Laplacian matrix. I will go back to this theorem hopefully today and prove an equivalent theorem to this in a slightly different way. So as I said, there are many things about this model, very well studied model, that I'm not going to tell you about or even advertise. I'm going to leave you the fun of discovering that. But instead, I'm gonna discuss some, as I promised, some local and global properties of it. And again, I'm saying there, it may seem that this list is exhaustive, but it's just a few topics, small topics that I think are very interesting. So but first I want to, so I've explained more or less what are the words uniform spanning tree here in the title. Let me tell you what I think of what I think about when I hear the words local and global structure. So somehow it's easier to start with a global structure. So global structure, or the global geometry of the tree, is just are a bunch of questions of the form. Take two typical vertices. What is the tree distance? What is the length of the path between them? So this is the typical distance between a pair of vertices. You can ask this on any, of course, on any graph. Or you can also take the maximal distance between two vertices. This is somehow a more studied quantity, possibly because it has a nicer name, right? The diameter of the tree is just the length of the longest path. So this is the length of the longest path. Another quantity is height, seen from random vertex. So these are all just random variables that are real random variables on where your probability space is just a uniformly chosen tree when you have some underlying graph. So these are three questions, and it turns out that perhaps the ultimate question that contains all of these questions is whether the metric space, if you consider the tree as a metric space, does the tree considered as a metric space converge? And we know this in some instances. Of course, I didn't tell you what it means to converge, and in fact, I won't in these series of 3 lectures. I probably won't tell you what this really means. Just to say that it's the Gromov-Hausdorff-Prokhorov convergence. For those of you who know what it is, for those of you who don't, it doesn't matter at this point. But these are the kind of quantities, random variables that may be real or may take the values in the space of a metric space of metric spaces, for instance, and we're looking for their typical size or perhaps their limiting distribution, right? So this is one type of questions, and the other ones that I'm interested are. So this is the question when I zoom out and view the tree from outside as much as possible, and the other questions, of course, is what if I zoom in, to the very to as much as I can. So the local structure measures exactly the things that disappear in the global structure. And here's a bunch of question you can ask. Of course, what is the number of leaves? Leaves are vertices of degree 1 in the tree, or in general, what is the number of degree k vertices in your tree? How does that behave? Or what about or even a more sophisticated question is, what is the number of vertices in the UST such that the ball of distance 2 in the UST looks like something like this. Right? Completely legitimate question. Right, this is the vertex V. This is where it rooted, and if you look at distance 2 in the tree, so all the edges and vertices that you can reach by path of length 2, you see a structure like this, right? Or any other thing that I put instead of this. Of course, this is just an example, and if you and the ultimate question here, right, in the global structure, the ultimate question was the metric space convergence, which will answer all of these 3. Right, I guess perhaps it's not clear why if the metric space converges, you know the answer to the 3rd question, but that's fine. So here the ultimate question is known as what is the local limit of the UST, and this answer essentially encapsulates all the possible answers, all the answers to all the possible questions when you replace this particular graph and this particular radius by anything that you want, so you know how to answer all of these questions at once. Of course, you kind of get the feeling that the number of leaves would be linear in the number of vertices, just because the average degree of the tree is 2. But of course, this is not always the case. For instance, if your graph that you started with is just a cycle, right? Then you would have just 2 leaves. But we will see, several answers to several of these questions in this mini course. And in the case of the complete graph, see Luigi Adar from earlier this summer for an extensive treatment, but I think Luigi spoke about minimal spanning trees. Oh man, I can't hear you. You're muted.
Yeah, he spoke also about the uniform tree.
Okay, so
in the case of the complete graph.
Okay, so let me just tell you then, let me tell you what happens on the complete graph just as a case study for this. So case study for these questions, case study is the UST on the complete graph. And I guess I should say, as Omer said before, please feel free to stop me at any point. I admit that I'm extremely tired. I've just put to bed my two girls and they're still up. So that means I'm not very concentrated, and it's most likely that I will make several mistakes due to that. So please feel free. So let's answer some of these questions in the case of the complete graph, or just to show you what could be the typical answers. So this is a claim that is actually easy to prove, and I don't attribute it to no one because I don't really know who is this first who first proved it. So now we're in the complete graph, where we just draw out of all the n to the power n minus 2 trees, we choose one at random. X and Y are two different vertices, and we ask what is the probability that the tree distance, i.e. the length of the path, the unique path between X and Y in the tree, so T is the UST of Kn. What is the probability that this is at least some constant times square root of n? So square root of n turns to be the interesting, the correct order of magnitude of all the typical distances, and this is not so hard to see that this is the answer. Even though if this is the first time you hear about the UST, then this is not immediately clear how to do. You will need to understand that this path between X and Y is distributed as the loop erase random walk, which I will probably only discuss in the third lecture, if at all. So the typical, somehow, if I choose two random vertices, or because the complete graph is transitive, I could choose, because of symmetry, I could choose any two fixed vertices. But if you want to look at the height, this is actually a difficult question. So the Erdos and Sekeres proved in '67, this is one of their most famous papers, that if you look at the height, by the way, did I say what the height is? Height seen from random vertices. So what this means is, yes, Rick?
No, you didn't say what the height was.
I didn't say. So some people call it radius. I mean, if you choose a random vertex and you look at the minimal R such that this radius captures the whole graph. Okay, so it's not the diameter, and of course it's not the typical. It's distance between pairs of vertices is just another quantity, and they found out that the height divided by square root of n converges in distribution to some continuous random variable supported on 0 infinity. And in fact, there is an explicit density function that you can write for this thing. So this was in '67, and it's a counting argument and a bunch of generating functions. And the diameter, which is a somewhat more natural quantity to look at, but turns out to be somewhat more difficult to analyze. So this was something like 20 years later. Sekeres proved that the diameter of, again, this uniform tree on n vertices converges in distribution to some random variable with the following density function. As right, the y is just I'm not showing you this, Rick. I can see your mind working. I'm not showing you this this formula tells you nothing, right? I don't understand, and I don't think Sekresh understood what is this formula really tells you. It's just something that comes out from extensive use of generating functions, which is, of course, no one recommends for your sanity. So this, I just wanted to show you that that there's an explicit density function, and we understand this density as much as we possibly can. And this was the status in the early 80s. In the 90s, right? The ultimate theorem has been proved by I guess this is in the early 90s. By Aldous, and Aldous introduced the limiting object, and I have to mention here Lagal as well. So this is something between 90 and 93, several papers, and this in fact reproduces all of the three theorems above, and in fact gives you something much stronger. And it tells you that if you look at the metric space. Right, it's a metric space on n vertices, or a discrete metric space on n points. You take the distances, right? You divide them by square root of n, and this converges in distribution with respect to a topology that I'm not telling you anything about except for its name, Gromov, Hausdorff, Prokhorov, GHP, to an object that is now very well known and understood, called the continuum random tree. So this is the continuum random tree, also known as CRT. This is the term that Aldous introduced, the CRT. Of course, if you Google now CRT with all the politics involved in it, critical race theory, so you will get, of course, much more hits than you expected to. So this is indeed this is evidence that the continuum random tree is a very interesting topic, even outside of math. And here's how. So I'm not going to define to you what it is exactly. Well, I guess I am, but because I'm just going to tell you one way of constructing it. It's a very interesting object. Here's how it looks. This is a sample of this tree by Igor Kortuchemsky. And as you can see, it is some sort of a fractal. Let me tell you how you draw it, just in case you're curious. So what you do is you start with the real line, the real ray, and you put a Poisson process with intensity Poisson process with intensity TDT. Right? So at T you have at time T you have you have this density. So you have a bunch of points that become thicker and thicker on the plane. And now what you do is this is the line breaking construction. You consider all of these finite spaces. You consider just them as a bunch of order sticks, stick breaking, not line breaking. And you have a bunch of sticks, and you just put them together. So this was the first stick. I put it here, and then I take the second stick. I choose a uniform point on the first stick. Let's say it was this, and I hang the second stick. And now I have the third stick, and I choose a uniform point on the aggregate that I've built so far. It has finite length, so just choose some point, perhaps it's here, and I put that, and I continue in this way ad infinitum, and it's a theorem that in fact this thing converges and creates to you a random compact metric space, right? There's nothing goes to infinity in this in this construction, and indeed between any 2 points, there's just a unique geodesic, and so it's indeed a metric space. Okay, and of course it's random because here's your probability space, right? It's determined by this Poisson process, and this is just one way of constructing this thing. But by this construction, Aldous was able to understand these two theorems in a much deeper way. So in fact, when you consider perhaps the classical construction of the CRT simply by you draw the tree and you look at the path going around the tree, you can easily deduce. So a corollary. Perhaps I didn't explain this very well because this is not the focus of my talk, but you can immediately get that if you look at the height of the tree divided by square root of n, then this converges in distribution, as I said, to some continuous random variable with like a peculiar density. This one I didn't show to you. This converges to a square root 2 times the maximum of ET, and ET is the standard Brownian excursion. So it's a Brownian path conditioned from between time 0 and 1, conditioned to be non-negative throughout its lifetime, and its diameter is just a slightly more complicated, but not very difficult functional of the Brownian excursion. Somehow the Brownian excursion is this path that I've explained to you that winds around the tree, and these two formulas can be easily deduced from this convergence statement. 0 here, and this is just minus twice the infimum between them. So you have here the supremum over the choice of 2 points between 0 and 1, T2 and T1. T2 is bigger than T1. You look at the excursion at time T2, add, right, this is positive, add the value at time T1, and subtract twice the infimum of the excursion and between them. So what we learned, so this was deduced in the 90s. So what we learned in the 90s by Aldous is that if you look at this fairly simple functional of the Brownian excursion, this is its density function. And surprisingly, up to 2015, before a beautiful paper by Wang, this was the only way to deduce what is the density function of this, completely question that trees are completely irrelevant to it. You have a Brownian excursion, some odd looking, but completely legitimate functional of it. Here is the density function. The only way to prove it up to 2015, mind you, was going through random trees. Turns out that there are many other quantities like that this is the only way to reach. But now we know Wang gave a direct proof of this fact. Okay, so so this is what we know about the global structure. Let me tell you what is known about the local structure, perhaps more briefly. And again, please stop me if there are any questions or comments. I'm going to briefly describe just the history. Again, we're looking at the UST of the complete graph. Right, this is my tree, and we're interested in the local structure of it. So the number of leaves, the number of degree K vertices, and actually these two quantities are actually much easier on the complete graph, just because there's so many ways of sampling the uniform spanning tree on the complete graph itself, right? Not so many ways of sampling it, and one of these is using prefer codes. Probably not mispronouncing it right. And if you follow this bijection given by prefer codes, you see that the degree of a vertex, degree in T, is just equal in distribution to the binomial distribution with these parameters plus 1. can't really be binomial, right? Because the degree will never be 0. It has to be bigger than 1, and this is it. So you see that it really does converge to a random variable, which is 1 plus Poisson 1. This is just the degree, but what about the other types of questions, right? How many vertices does the local neighborhood of radius 2 look like that? And this was answered by Jeffrey Gramets. So this is the ultimate theorem for the local structure, ultimate theorem due to Gramets. And what he showed is that the local, and I'm not even going to define to you what is the local limit, but just tell you what is it, whether you know what it is or not, and more importantly, how can you get the answers to let's say this particular problem? What is the density of the number of vertices that look like this? So Gramets' theorem is that the local limit of t, right, as n tends to infinity, is the Poisson 1 branching process. So BP will always be a branching process in this talk, branching process, conditioned to survive forever. Conditioned to survive. So of course, Poisson 1 branching process does not survive with probability 1, but there's a fairly natural way of defining it, and let me tell you what it is, or how to sample it instead of telling you what is the conditioning. It doesn't really matter. You just start with an infinite discrete array on the natural numbers, and on each of these vertices, you hang a Poisson 1 branching process. So it's just a little avenue with a lot of trees, just like so many streets in Vancouver are. Oh, how I miss Vancouver. Right, so this is how it looks like, and now you can immediately deduce, right? So a corollary, right, or a bunch of corollaries. What is the probability that a vertex is a leaf, right? Which is either a random vertex or a vertex, a single vertex, right? You just have to, right? You just have to have the first progeny of your branching process of the first particle on the tree, right? You just have it. You must have it 0, right? You cannot have any particles there, so it will perhaps look something like this, right? This tree, right? And so here, so for that to happen, the first generation must die out. The first generation has a Poisson 1 distribution, so this is just 1 over e. So what this tells you, in annealed rather than quenched way, this is not very difficult to obtain, is that the number of leaves is n times 1 over e, and 1 plus little o of 1 with high probability. Okay, and similarly for degree 2, of course, so in particular, of course, the degree of the root is just distributed as a 1 plus Poisson 1 random variable, as I hope. But also, if you want to figure out what is the number of vertices that your structure, your tree looks like this when you look at this vertex, this is right. So if it's in this question, I have to have the number 2, right? I have to tell you that I'm looking only at radius up to radius 2. So this must have been a part of the infinite ray that I've defined. So that means that the origin, right, V has to have 1 progeny, right, and this one has to immediately die out, right? So this, having 1 progeny costs you 1 over e, or e to the minus 1. So for this one to die out costs you another 1 over e, and this one has to die out as well, right? Its progeny has to immediately die. And this one we can do whatever it wants, right? Because we're only looking up to level 2, right? So perhaps this has more children or not. We don't know. It definitely has 1 other child, right? Because it's an infinite connected graph, right? I'm not going to draw it. So this number has to be of order n to the n over e cubed, right? And Right, sometimes it gets a little bit more complicated if you actually want to do calculations, because when you look at this picture, of course, you don't know exactly which was the infinite branch, right? It could be both of them, but it doesn't, right? It doesn't really matter, right? The first progeny has to have one child and then another one, right? So that costs you e to the -2, and the second one has to die out immediately. The third one we don't know, so in fact this has the same density. And with this way, of course, you can compute whatever fixed rooted tree I give you. You can answer the question: how many vertices, or what is the density of vertices that you will see this exact fixed tree as the ball of distance are around them. Okay. So this is the state of the art on the complete graph. And of course, there are many other more delicate questions that I've not been that I haven't mentioned. Right, Jeffrey's theorem is from '81, so it's indeed ancient history. Apologies, Jeffrey, you're not that old. If you're here. But of course, all of this story was very general. All this that I've told you was for the complete graph. What can we say about other graphs? So other graphs that I mean are other natural, good-looking graphs that we encounter in our day-to-day life. So some graphs that I'm interested in are the hypercube. 0, 1 to the n, or z n to the d. I'm only considering in this mini course finite graphs, and I will not consider the deep theory when you take infinite limits, right? And many others. But as you can see, so even right here, d bigger than 4 is what we're able to say something about. And indeed, in all of the graphs that all of the story that I will tell you about are going to be graphs of high dimension. So it will definitely not be for the 2-dimensional lattice, right? And you will hear nothing new about the USTs on this graph in this mini course. I see the number of participants dropping. So let me tell you the results, and I will tell you the results in some calligraphic style, just because I don't want to burden you. As I said, it's quite late here. I don't want to burden you with definitions. So here are the things here are some things new that we can say. So I will try to present some of the proofs. Hopefully, for one of the results, I will present a complete proof, I hope, tomorrow and today. So here's one of the theorems. So again, I'm not really going to tell you what is a high-dimensional graph. I'll just write a bunch of examples, expander graphs, and there are more. So just to you could take it for, if this list of 3, in fact, it's an infinite list if you consider this, does not satisfy you, then you're very welcome to open the paper and take a look. So the statement is the following statement: for any high-dimensional graph sequence, right, i.e. this list at least, and some more, right? And the important thing here is the d bigger than 4, because 4 is the critical dimension of the UST. For any epsilon, there exists some number such that the diameter of the tree is at most diameter of the uniform spanning tree. So again, T is the UST of Gn, right? There's n at the background, right? Is at most, n is the number of vertices of Gn. So the diameter is of order square root of n. Right, so this is one result that I will tell you some parts of the proof. It's actually turned out to be a little bit difficult, more difficult than we anticipated, because it is much easier to understand in this setup. Why is an expander a high dimensional? I don't want. In high dimensional, I don't mean the dimension in the algebraic topology setup, but rather to mean that because in that it is very highly connected, meaning that the random walk mixes very fast on this type of graph. And the reason that we call it dimension is because the probabilists of, are thinking of, low dimensions as dimensions 2, 3, 4, or any finite number, and high dimension on lattices in these dimensions, right? And the high dimension, we just mean a lattice in high dimension. So in some sense, when you take ZD, take D to infinity, it has the behavior of an expander, okay? But I definitely do not mean all of these high dimensional trees that you and I and Rick and many other people are interested in. Okay, even though one of the theorems that I will tell you about has an extension to these high dimensional trees. So I hope I answered your question, Doron, and confused you at the same time.
And
you did.
So, so the theorem is that this holds uniformly for various classes of graphs, GN?
Yes, as long as the high dimensional parameter is above something. Yeah, so it's
so it's just a single parameter.
Yeah, well, there are actually three. There are three parameters if you want to.
Okay.
Okay, you just take the maximum or minimum of them, and then it's just a single parameter if you want. So as I said, so this is one theorem. And of course, the natural question to ask, okay, you guys, are you lazy or are you dumb? Can't you prove what is the real limit in distribution of these things? And I guess the answer would be the latter rather than the former. And here's a work in progress that hopefully we will release at the end of this summer. So this is together with Eleanor Archer, who just started her postdoc here at Tel Aviv, myself and Matan Shalev. All right, so what we find is with the same setup, there exists some fixed beta such that the beta times the diameter of Tn, right? So it's the same random variable divided by square root of n converges in distribution to the diameter of the continuum random tree, right? So you look at, so this is particularly, for me, it's particular. Choose your favorite graph. Mine is definitely the 5-dimensional torus, right? So this is the graph that I'm more interested in. So here's a theorem. You take the 5-dimensional torus, draw a uniform spanning tree, look at its diameter, then it converges up to this scaling factor of beta. And then the limiting distribution is this functional of the a Brownian excursion, right? This thing with that peculiar looking density function. Okay, so this is one of the works in progress
wasn't this known for the torus?
No. No. In fact, I don't know of any example, or at least non-trivial, except for the complete graph where the diameter of the UST, where it was known the actual limiting distribution. Not for the torus, not for the hypercube or expanders, as the proof is completely oblivious to what exactly is the graph, as we expect is the graph that we're looking for. And in fact, as what we actually prove, we don't just prove the theorem about the diameter. In fact, what we prove, as you can expect, what we prove is that if you consider this metric space the metric space induced by the spanning tree, right? The distance is just the length of the path between the point. This converges in distribution with respect to this Gromov-Hausdorff-Prokhorov topology to the CRT. Okay, this is our theorem. And Omer, if you come to Lumini in January, I hope to tell you more about this this particular result. I'm not sure how much if I'll be able to say more about this here. And the theorem that I will try to tell you some things about today. So this, as I said, so this is the ultimate theorem, as I said before, regarding the global structure. Here is the theorem concerning, so this was global. So this is global. And this is the theorem, only theorem that we have about the local structure, and this is together with with Yuval Perez, right? And this is here is the statement. So Gn is just a graph sequence with that is regular.
Asaf?
Yes, please.
I didn't understand the Omer question about the uniformly in the graphs. So that beta, of course, it's a parameter of your sequence of graphs, right?
So Omer asked about the first theorem where there is no beta.
No, in the second one?
So in the second one, of course, beta depends on the sequence of graphs.
Okay.
And there's a way to express it in particular. So if the graph is a part of the class that we're discussing and has the very high degrees, like the hypercube, then this will be 1 typically, right? It has this theorem. So for instance, beta is 1 when you plug in the complete graph. And beta is not 1 if you look at my favorite graph, the 5-dimensional torus, and there's a way to explicitly say what it is. It's some probabilities of random walks non-intersecting, which is positive in 5 dimensions and above. But it's slightly more complicated than that. It doesn't really matter. Let's see what else is in the chat. Are there any known examples that are outside of domains? Thanks, Jaffe. It's yeah, as I said. So there are many examples, but the most in fact, okay. Let me put it this way. There aren't many examples, but the example that we do have are unfortunately the most interesting one. So indeed, on the 2-dimensional lattice and the 3-dimensional lattice, the CRT has nothing to do with the uniform spanning tree. So this is kind of like interesting to just note that this picture, obvious, but this picture is very far from this picture. Right? How would you notice that just by looking at the picture? You don't, but an old theorem of Rick tells you that these are in fact very different, right? Rick's theorem tells you the distances between the typical vertices. Spanning tree on a cycle. Sorry, so this is another example is a cycle, but okay, let's take even a more interesting question. This behavior, of course, on 3 dimensions is of course something Sarai can tell you much more about. Is in fact much more difficult, and the exponents are not known to the best of my knowledge, right, Sarai?
Not the exact value. Yeah, just some bounds.
There are some bounds, right? But it's not clear what is the diameter. Sorry, so perhaps since this raised some question, are there any further questions about the 2 theorems that I stated? Let me tell you something about the last theorem, and then I'll give you some proof of something that is very cute, in my opinion. Gn is a graph sequence. It is regular, meaning all degrees are the same, are equal to each other, and the degree tends to infinity. Right, so this is does not capture the torus of a fixed dimension in any way, but this theorem is about the local structure. Then the local limit of UST of Gn is again the Poisson 1 branching process condition to survive. So if your favorite graph is the hypercube or any expander of high degree, it doesn't even have to be an expander, right? It could be the most low dimensional graph. You know that, and low dimension, there's nothing wrong in being a low dimensional. I'm extremely glad. And this is curious, right? Because here you see that in the local structure, you see a universal behavior regardless of the dimension, as long as the degree tends to infinity, right? So somehow we don't see this critical dimension phenomena when we're looking at the local structure. And in fact, that this theorem I hope to show you a complete proof of. Again, I just because I planned the rest of this mini course to just show you the proof without any further ado, unless anyone has any further questions about about the proof, about the statement. I will, in the last 10 minutes, I will show you Kirchhoff's matrix tree theorem rephrased in words of in different words. Okay, and this is in fact what I'm showing to you is the way that Kirchhoff wrote his actual matrix tree theorem, and the one that we know very, very well is actually a corollary of it, and is not their equivalent. It's not actually stated in his original paper in German. What you see is what you're about to see here, where he also defined the concept of effective resistance in an electric network. So here's the theorem, and the proof is based on this theorem, 1847. So it's kind of nice. This is probably the oldest modern statement that I have. You have a finite connected graph. E is an edge xy, right? And T is a sample of the uniform spanning tree of G. And you're asking yourself, what is the probability that E belongs in this tree? So it turns out that the answer is the effective electric resistance between X and Y in the graph, right? So I'm just reminding you very briefly, and you can read more in the link that Omer posted in the abstract. If you've never seen this quantity effective resistance, you just send a unit current flow from X or from any two vertices. They don't have to be an edge. So this is an anti-symmetric function on the vertices, in which the mass going in equals the mass going out for every vertex that is not X and Y, X or Y. And from X you have unit current flowing out, and into Y you have unit current flowing in. It's a current, meaning that no electricity goes in a cycle, and this determines a voltage. This induces a voltage between X and Y, and this voltage difference is the effective resistance, right? But it turns out that this quantity, I'm just as a side remark, this effective resistance has been invented by many different people, in the old days. So it's called, in complex analysis, they call the same thing extremal length. In other places, they call it modulus. And it's essential. Sometimes it's the inverse of the effective resistance. And it's all kind of, it came up in complex analysis and potential theory and probability. And it all kind of encapsulates the same thing. It's a very interesting quantity. It has many kind of many connections to many fields of math, and it always surprises me, even though I'm in this business for a while, that there are new things to learn about this about electric networks. And in fact, this theorem that I'm about to show you here can be seen just as a new fact about electric networks that I will show you tomorrow. Today, I will just tell you about a nice proof of this fact. So here it is. So I'm going to define to you the electric current between X and Y, right? So I told you what it is, and here it is. So theta E. I have to tell you what is the value on each directed edge, and it's just going to be the probability. So I have a tree, a uniform spanning tree drawn at random. This theta E is the probability that the unique X to Y path in T uses E in the correct direction, right? Minus the same probability, just that it uses E in the incorrect direction. Okay, all directions are correct, but this I defined to you an anti-symmetric function. And the claim is that theta is the unit current flow. Right, and let's just make sure that it is indeed unit. And this is easy, right? Because we have, this will be true even if your tree is fixed and not random, right? Because just because there's a unique, only one edge coming out of X and going into Y, right? So you'll have just one, just one edge that receives one here, and 0 here coming out of X, right? And for Y, it will be the other way around. So it's definitely unit. And why is it a flow, right? For the same reason, right? For any other vertex, right? And now you have a fixed tree, right? T. For any other vertex, either the unique path between X and Y, for any other vertex V, either the unique path goes through V, right? And then it has one edge entering and one edge leaving, right? It's a simple path, right? And which will contribute 0, or it does not go through V, and then both sides will be 0. So it's obvious that this is a unit and this is a flow, but the fact that it's a current flow, meaning that if you look at any cycle, the sum of theta will cancel out. This requires some thought. So let me tell you. So right, this holds and this holds. So why does the cycle law holds? Or in other words, for any cycle, we have to show that theta of EI, right? So this is a directed cycle in your graph. We have to show that this is 0. And let me just convince you by a simple bijection that this holds. So this I can always write as the sum over T, which is a spanning, so little t is a spanning tree of G, and the sum over I from 1 to M of Fi plus T, right? And this Fi plus T is just +1 if EI is used in X to Y path in little t, and 0 otherwise, right? Minus the same thing, Fi minus t, right? So I just expanded this quantity here, and I want to convince you in 2 minutes that these two sums are equal, right? The sum in each of them, I'm summing over all spanning trees, then over all the edges, +1 if I'm using the edge in the right way, in the path, in the unique path from X to Y, or -1 if I'm using it in the wrong way. Sorry, we already said all directions are, there's no right or wrong direction, just in the other way than intended. So let's just verify this. So take two further seconds. So let's just show you the bijection. I'm writing it formally just to convince you that it is correct, and then I will show you what it is intuitively, even though formally is somehow better. I'm looking at all the pairs Ti such that T is a spanning tree. Right, spanning tree, and Fi plus T is 1. So I'm using EI in the right direction, and Ti similarly uses the other way around. So what I want to show you is that if I look at this union, right? This is all disjoint. Disjoint union, of course. Right? If I look at this union from 1 to m, then it has the same cardinality as here from J, from bit J from 1 to m. I'm writing it slightly different. So what is the reason? And of course, if we know this, this tells us that these two things are equal. So here's the bijection between the two sets, right? So if Ti is in the first one, so I'm using, so here's the, let's draw the cycle in red. Right, and this is EI, right? And the path between X and Y uses it. Perhaps it goes like this, from X to Y, right? The T, if I remove EI, right, in any tree, if I remove an edge, I get two connected components. There's two connected components, right? And so I can go over the cycle, right, in its original direction and wait after EI, right? So I continue going on these edges until I find the first edge that connects the two connected components that I've received, that I got by removing EI. So let's do that. So let the EJ be the first edge after EI in the cycle that connects these two components. I add that edge and I get a new tree in which EJ in the path between X to Y is used in the opposite direction, right? T minus EI and plus EJ, right? And J belongs to TJ minus, right? And this operation that I remove one edge and add another one in the cycle is completely reversible, right? If I start with the graph where the tree where EI is removed and EJ is there, and I want to go the other way around, I just go the other way around. I erase EJ, right? I get two components. This time I go the opposite way in the cycle until I reach EI. This has to be the first edge that connects the two components. And I add them, right? So this gives you a bijection between these two sets, and this shows to you that theta was indeed the unit current flow. Now you look at the edge xy, right? This was the current flow, right? So, right, any current flow induces a voltage, and the voltage difference on the edge is just the difference between the 2 points on the edge. Right, so since X and Y are right, since X and Y is an edge, there could be several edges between X and Y. What you get is that this is what's written on the edge, right? It's just the voltage difference, and hence it is the effective resistance, right? So and this concludes the proof. So what I'm going to do, in tomorrow's talk, I'm going to show you more cute facts that it's very well possible that even if you are familiar with effective resistance very well, you do not know these facts that will prove to you this theorem. So the next talk is going to be a talk about fun facts about electric networks that perhaps you don't know, because I didn't know them, but who knows. So I will see you tomorrow with that. Thank you.
Thank you, Asaf. Yes, so we can have questions from anyone, and I will soon also stop the recording.
Is this what Kirchhoff